Okay, so I'm gonna test this out with just recording because I wanna do a couple of problems and then read a book. So I don't wanna go in and out of stream all the time. And I just wanna finish the blind 75 list so I can focus more on the stuff that I don't know. Given an array of distinct integers, candidates, and a target integer target, return a list of all unique combinations of candidates where the chosen numbers sum to target. You may return the combinations in any order. Okay, so I have an array of distinct integers called candidates. And a target integer target. Return a list of all unique combinations of candidates where the chosen numbers sum to target. Isn't that very similar to the threesome or two-sum? I think the only difference here is that this is an arbitrary number. The same number may be chosen from candidates an unlimited number of times. Okay. True combinations are unique if the frequency of at least one of the chosen numbers is different. God damn, yeah. So this makes it a lot harder, I think. It is guaranteed that the number of unique combinations that sum up to target is less than 150 combinations for the given input. I have no idea how I should do this. The problem is how I'm gonna know how many times to test each one. That's the issue. I think I'm gonna change this music. If it was all combinations of the items in the list, then I think I can use the choose sum logic, where I have two pointers and then I update each one and check to see if it is hitting the target or not. But this the same number can be chosen an unlimited number of times. Because the question is if I can test, because I'm gonna have to test all of the numbers. I should see, maybe I should test if they're divisible, but then I can have all possible other combinations where I have different numbers at different frequencies that can also add up to the target. So I don't understand really well. I can't think about a way to fit this in an algorithm. can I think about the brute force approach, which would be, but then it's still even the brute force, because I don't know how to check how many times should sum each one of them, or how I'm gonna do that in the computer, the logic of the algorithm. I mean, maybe what I should do is just try decrease the, yeah, but even then, because if I select one number of the list and decrease from the target to find the other ones, I still can't think about a logic to decide how many times I'm gonna get each specific number in order to form the combination. Two combinations are unique, the frequency of this one is different. I don't want to write things down because I know that the solutions that I'm thinking, or the progress that I'm thinking, let's say, is not gonna solve the problem, and it's probably not the right approach. As so far I thought about the 2 pointers, the stuff to testing each particular number one at a time, dividing the target and getting the remainder of the division or the quotient, and doing that, using that to figure out, but then it still leaves all the other options open. It feels to me like there's some mathematical trick here to figure out all the combinations, all the ways to combine and sum into combine numbers into summing into another one. But I'm not aware of this trick. Or is it because I don't understand what backtracking is? From what I remember vaguely is something using a cache or something like that, or a hash to keep track of used values, so maybe I should think about something like that. I also think maybe it involves recursion as well. Or maybe the array is sorted as well, so I can use that to eliminate some numbers. The biggest issue is that I keep following the same logic even if I eliminate, because it's gonna be the same problem but with a shorter array. And the biggest key here that I'm not being able to come up with is how to create the logic to test all possible combinations. The frequency of the numbers is... I can't think about a way to do that. Even if I try to brute force, because there would be no way to previously set a fixed amount of times that I'm gonna use each number to test all the possible combinations. Or maybe what I can do is... Oh, but if I remove the... Yeah, I think it's gonna have to be a recursion or something like that. But then how do I... Oh, I think I understand the logic. I create a counter and then I pass all the values of the list into this counter. And then I keep track, and that's why it's backtracking. I keep track of each number that I used and subtract from the target. But then how I'm gonna know the unique combinations? I have to be through the mapping, but I'm not sure how. So there's one. I don't think I'm gonna be able to solve it in 20 minutes, just not enough time, but the one approach I'm thinking, the split I'm at right now is whether or not I should translate the list into a hash first and then do some recursive call to keep track of the numbers in the hash, keep track of the numbers that I'm using through the hash. And then based on that, I can figure out the combinations. So maybe I will need 2 different lists. So let me think about the names. Comb. I can use a hash to keep track of the combination of specific, but then how do I find... The key thing here that I'm stuck at is how do I differentiate different combinations? Because if I use a hash map and then I put this hash map on another list to keep track, I don't know how to compare. I would have to compare all the key values. Maybe that's the way. But then it feels like it's gonna be too big. But I think that's one possible solution, now that I think about it. So you have a hash map, you have a list, another list. We translate the first list into the hash map. So each key has a value. Each item in the list is a key value in the hash. And then you go over the target and you find a combination that reaches the target and put the combination in the hash map. So each item in the list is the key value, and the value of that key is equal to the frequency of the number, how many times you use that number. And then you pass this hash combination into another list, and then you do that recursively, and each time you compare to see if the object that you used is already on the list or not. But the issue is then, how would you know? The problem is the logic, because how would you create a different... Well, there are several optimizations here that are kind of difficult to think about. Because how would you know to test a unique combination each time? So maybe you could eliminate... Yeah, that's one optimization, I think. You could eliminate from the original array, or you could check the hash, you could check the list with the previous solutions each time and eliminate these possibilities. But then, how would you do that? That's the hard part. Probably have to separate the logic into a function, the logic to find. That's the tricky part. Yeah, this would translate. Then I would create a different function there outside. Finds comb. I'm gonna pass candidates, targets. And then here I would probably use something like 2 pointers. But then it's also tricky because you can use any frequency. That's the most difficult part. I think this function I would call recursively with a different list each time. And inside this frequency, it would update the hashing based on how many times you used each item. And maybe here should be 0. Initialize all of them with the 0. And then each time you use one, you increase the value in the hash of that item. And then at the end, you append the hash into the tested comms. So first thing is probably to check if. So here I would have also combination equals none, which would be the object. Maybe I should put combination. Should not confuse with this one. If this has to be combination because it's one combination. Not in comb. No, if combination in comb. It has to be in tested comms actually. Oh, so maybe I don't need this thing here. Maybe we can just do if comb in tested comms. I put pass. So it first checks to see if the combination already exists, and if it does, it passes. Then performs the logic to see if the items reach, and then I probably need to figure out a logic to change the candidates list each time I use an item, so that I can test a unique sum each time. I think that's kind of the track to solve this, but obviously I'm not gonna be able to solve it in just 20 minutes. But that's what I want anyway. I just want to go through the process of thinking and figuring out roughly what's the logic to use. So later on I'll go dive deeper into this. I'll be right back. Alright, time to look at the solution.
Hey everyone, welcome back, and let's write some more LeetCode today. So today let's solve combination sum, and this is another problem from that blind 75 list. The link will be in the description, so we are doing one more problem and have very few problems from this list remaining. So we're given an array of distinct integers called candidates, and we're given a target integer called target, and we just want to return a list of all the unique combinations of candidates where all those numbers end up summing to the target value. And we're allowed to return those combinations in any order, and we're also allowed to use the same number from candidates multiple times, but we don't want to have duplicate combinations. For example, if 2, 2, 3 sums up to 7, right? That means 3, 2, 2. These are the exact same values, right? Just in a different order. These sum to 7 as well. So we don't want to add both of these combinations to the result because they're the exact same. So what we're saying is we want combinations. We don't want permutations that end up summing to the target value. So in this example, you can see that we are given these candidates and a target of 7, and we have two different ways that we can sum up to 7. Of course, 7 by itself does sum up to the target, and 2 occurrences of the 2 value and 1 occurrence of the 3 value added together are going to lead to 7 as well. So then we return these two combinations as our result. So I would say the difficult part about this problem is trying to figure out how to eliminate duplicate combinations, right? For example, if we just brute force it like a decision tree, so we have 4 different values we can choose each of them an unlimited number of times. What we can do is have 4 decisions in our decision tree, right? Like that might be the naive thing that you start with. So we would get 2, 3, 6, and 7, and then we'd basically continue that, right? On one path over here, we would find, okay, we found the 7, so we found the target, right? So we found one way that we can reach the target. So therefore, we don't need to continue down here because as we add more numbers, all of these values are going to be positive. So as we add more numbers, we're only going to get a sum larger than the target. So, I think it's kind of obvious why we don't continue down this path, right? But down here from the 6, let's try to continue, right? We can add a 2, so we'd get 6, 2. We could add a 3, so we'd get a 6, 3. We could add another 6, so we'd get 6, 6. And we could add a 7 where we'd get 6, 7. So notice how all of these are going to sum to a value greater than the target. So down this path, we never ended up reaching the target. We only went over the target. So we don't continue down any of these paths, right? But now let's continue down this path. So here we can get another 2. We can get a 3. We could get a 2, 6, but in that case, we would get 8, which goes over our target. We could also get a 7, 2, 7, but that also goes over our target. Now, here's the part where we're going to end up getting duplicates. So I'm going to show you why this type of decision tree does not work. So here, we could get a 3, for example, right? So we'd get 2, 2, 3. Now, that sums to the target. Down this path, we could choose a 2. So we'd get 2, 3, 2. Notice how both of these end up summing to 7, but they're the exact same. They're just in a different order. We have 2 2s and a 3. Here we also have 2 2s and a 3. So we ended up getting the same one twice. So this works in finding the combinations, but we end up getting duplicate combinations. So what kind of decision tree can we try that gets us the result that we want, but does not have these duplicates? Let me show you how we're going to do that. Let's logically think about this. We know that we have one value in our candidates, 2, right? So we can try to get all combinations that include this 2 value, right? And see if any of those combinations leads us to the target value 7. Now, we could also... So then if we make a second decision over here, right, in this decision, we're definitely including at least 1, 2. Now, if we go down this path, we want to make sure that none of the combinations down this path ever match the combinations down this path. How can we guarantee that? Well, in this side, we said we're definitely including at least 1, 2. How about in this side, we don't include even a single 2? So basically, we skip 2. So here we're going to have an empty array because we skipped the 2, right? All we said is we were able to start from here, but we said, no, we're just not including a 2. We're just going to do combinations with these 3 values. That's going to guarantee that none of the combinations on both sides are going to be matching. And that's basically the logic that we're going to follow. So from here, remember, we can include multiple 2s if we want to, right? So one decision here could be including a second 2. So we get 2, 2. Now, this path is going to include all combinations that include at least 2 2s, right? But remember, our definition for this decision tree needs to be recursive, right? Because we don't want any of the combinations down this path to be the same as any of the combinations down this path. So what we said here is we're going to include 2 2s. How about down this path? We say that we're not including any more 2s now. What we're saying is we had 1 2, but now we're done. We're skipping 2s. Now we're only going to use values from here. So that's the recursive thing, right? We're basically doing the same decision down here as we did up here. So here we're going to say we ended up skipping the 2, and we still only have one single 2. And so let's just continue to repeat that. So over here, we're going to add another 2. So we'll have 2, 2, 2. And over here, we'll say, okay, now we're done with 2s, right? Where we're going to keep ourselves at a limit of 2 occurrences of 2. And we're basically going to continue this logic until we get to our base case. So over here, you're going to see if we end up having 4 2s, we'll get a target of 8. So therefore, we went over our target value. So we're going to stop. But down here, right, this was our path where we said, okay, we're not going to include any more 2s in this path.
So I think I understand the thinking here. So he's going to do it recursively and then put if else statements to see if the target is passed or not based on the frequency, and then he's going to compare that with the remaining elements in the list. But it still doesn't seem like it feels like there must be something more that is more optimal, but maybe I'm just maybe it doesn't. there isn't anything more optimal.
So here we can make a decision. We can add a 3, so then we'd get 2, 2, 3. So we're continuing that recursive definition. And so notice how we have 2, 2, 3. That's 7, so we did find at least one combination. But remember down now, if we make a decision to the right, we want to make sure we don't have any duplicates from here. So in this side, we decided to add 1, 3. How about down this path, we say we're done adding 3s. We're not even going to add a single extra 3. So this is going to remain as 2, 2. Now, I think it's pretty obvious that down here, since we're only allowed to add values 6 and 7, neither of these is going to end up leading to the target. If we add a 6, we'll get a total of 10. If we add a 7, we'll get a total of 11. Neither of these, both of these go over our target. So let's quickly run through the rest of the decision tree. So over here we said we added a second 2. So over here, we're not going to be adding any more 2s. So here we can add a 3. So we get 2, 3. And over here, we would skip adding 3s, right? So we're not going to add any more 3s. This is going to remain as 2. Now down this path, at this point, we have a total of 5. So we're only allowed to add values 3, 6, or 7. All of those are going to end up leading to a total of greater than 7. So we won't be able to find any solutions down this path. I'm just skipping and drawing it out because we're kind of running out of room. Now over here, what we said is we skipped 2, and since this path includes the one where we added a 3, so here we're not going to add any 3s, and so we're only allowed to choose 6 and 7. That's going to end up leading to totals of greater than, it's going to lead to either 8 or 9. Those are both greater than our target value. So here, we're not allowed to add any 2s because that's what this path was. So we can add a 3, or we can choose to skip 3 and add nothing. So here, since we're skipping 3, so we're only allowed to add 6s or 7. So here we can say, okay, get a 6. This path, we skip 6, so we're not allowed to add any 6s over here. And from over here, we'll say, okay, we can add a 7, which will give us the total 7, right? That's the target that we're looking for, so we did end up finding that. So that's our second solution that we found. Now, since this path is going to lead to combinations that do include a 7, this path cannot include a 7, but you notice how as we are continuing to go down right paths, what we're saying is, okay, we're basically removing the number of elements we can choose from, right? We're popping 2 initially over here. Then when we go down here, we're not allowing ourselves to choose 3. Over here, we can't choose 6. Then when we finally go down all the way over here, we're not even allowed to choose 7. So therefore, we have no choices left. So this is also going to be a base case because we ran out of elements. And the way we're going to be tracking which elements we can choose from is we're going to have a pointer. Let's call it I. And so initially, it's going to be here, which means we can choose any of these elements. As we pop an element like this one, we'd end up taking our I pointer and shifting it over here, which tells us, okay, we can only choose these elements now. So that's the main idea. This is going to be a recursion tree. Each recursion step, we can make 2 decisions, and it's pretty easy to code up once you can kind of understand this logic. Let me show you how to do that. By the way, the time complexity of this, you can see that our decision tree, we're making 2 decisions each time. So it's going to be 2 to the power. What's the height of our decision tree going to be? Well, each value in this is going to be positive. It's going to be at least 1. So the height of the decision tree can be at most whatever the target value we're trying to make it. So 2 to the power of t, where t is the target value. That's going to be the big O and big O time complexity of this problem. So we are going to do this recursively, but let's have our result variable, which is basically going to be global for the scope of this problem, because I'm going to define a depth first search function inside of our outer function.
I think my biggest problem so far in the common theme in all these problems is understanding how the recursion goes into the function. What I mean by this is if you have a recursive call in the middle of the function, how does it compute all the return values of that recursive call? Just like the explanation of that Olala gave me in the previous examples of a previous problem in linked lists about how it stays on the stack. I think I understand it now how it does that, because each time it calls recursively, you don't finish the execution in the bottom value of the recursive call, because you have all the other values previously that were added previously into the stack that you're going to go back to once the program goes back to that specific point. So let's say you're funneling options until you get to the final one in your recursive call. Once the final one returns and the program is emptying the stack, it's gonna encounter the other ones that were not finished before, and then it's gonna execute the function recursively again. So it's kind of like a symphony. It doesn't go just down and then up, or the other way around, I should say. It doesn't fill the stack and then at the end of the recursive call empties the stack again and goes back to the main execution. It fills up the stack until it gets to the end of the recursive call, and then as it's emptying the stack again, encounters the previous times that it called and didn't finish, and then it fills the stack in again, and then empties again, and then fills again, and it does this movement up and down as many times as it needs until all the possibilities of the recursive call are ended. And to think about this movement of going up and down and with the recursive, while you think about the solution, is the part that is really hard for me, because I think I still haven't fully understood exactly. I need to find a way to visualize better in my mind how the recursive call is working inside of the function. So when I'm solving the problem, I understand the breaking points of each call. And that's the thing that is most difficult, I think. And the reason why I'm having a lot of problem with this, problems with trees, and this problem here as well.
So a few variables we're going to pass into here. We do want to maintain which of the candidates we're still allowed to choose. So like I said, we're going to have a pointer I that's going to determine that. We're also going to have a current variable. We're only going to have a single occurrence of this. It's just going to be a list that tells us what values we have added so far to the current combination. For example, like we could have 2, we could have 2, 2, right? 2, 2, 3, et cetera, et cetera. And for the values in our current combination, we do want to have a total. So we want to be maintaining what's the total sum of those, because if it ever reaches our target sum, then we know we have found a solution. If we ever go over our target sum, that means we've reached the base case and we can't continue anymore. So in our DFS function, let's go ahead and define those base cases. We know the base case is if total ever ends up reaching target, that means we found the result. So what we're going to do is result.append. We want to append the actual combination, so we're going to append current. And since we're only maintaining a single variable list for current, we don't want to actually append current itself. We want to create a copy of it, because we're going to continue to use this current variable when we're doing the other combinations recursively. So we don't, because then we're going to be modifying it. So we just want to create a single copy before we actually add it to the result. And after we're done with that, we don't want to continue the rest of this function. So we're just going to go ahead and break out of it by returning. So that's the base case where we succeed. What's the base cases if we end up being impossible to find a combination? Well, one is going to be if I is out of bounds, meaning we can't choose any more candidates. So if I is greater than or equal to candidates, or our total ended up going over the target that we're trying to reach, that's a base case where we have to return immediately because we cannot find a combination then. Now for the actual recursive step, remember we have 2 decisions to make. We can choose to include the value at candidates of I, right? We can choose to include this value. So what are we going to do if we're including this value? Well, first of all, we're going to take our current values that are in our combination. We're going to take that candidate and go ahead and append it to our current combination, right? We're going to do that before we end up actually calling our DFS function. So we're going to call DFS, and what are we going to pass in? Well, we're including this candidate so we can potentially continue to include it, right? So what we're going to say for our index I that we're passing in is I stays the same, right? We're not restricting which candidates we're allowed to choose from just yet. So I stays the same. We pass in current because we just updated it right now, so we can go ahead and pass it in. And the total did end up changing, so we took our current total and added this candidate to it, right? So we can go ahead and pass in total plus candidates of I. So let me delete this line because we're not doing anything with it. But yeah, so this is going to be that first decision where we do include the candidate. Now the next decision is going to be where we can't include it. But after we call this function, we want to clean up a little bit. We ended up adding this value to our current candidates, our current combination. So we want to go ahead and pop that before we go down the other decision. And so once we pop that, we can go down the other decision. That's if we're not ever going to include this candidate. So for the index, we're going to pass in I plus 1, indicating that we can't include any occurrences of I. And for current, we can just go ahead and pass in our current combination. And total is going to stay the same because we didn't end up adding any value to it, right? We left our current combination as the same as it was before when we actually called this function. And once that's done, we basically made our 2 decisions, right? Can you see what's going on? Can you see that we called that for search once and then we called it a second time? So we did create that 2-branch decision. And after we're done with that, we can go ahead and return. And in this case, we actually don't need to return. So that is the entire DFS function. Last but not least, what we want to do is actually call it out here. So we're going to call it, passing in 0 as the beginning index, passing in an empty array as the current combination, and passing in 0 as the current total. And then once that is done, we will have updated our result, which we declared up here. And then we can simply go ahead and return that result. It should contain all of the combinations that end up totaling to the target. So you can see this problem isn't too bad to code. This backtracking approach isn't too bad once you kind of understand the 2 decisions that we're actually making. So I hope that this was helpful.
Yeah, that's the main problem I have. There's this call 0, like I said before. Right? It's hard for me to visualize the execution flow of the function when doing these recursive calls. And what exactly is going to be passed, when it's going to be stopped, when it's going to return to previous values that it didn't solve fully. So appends a copy of currents, which is a list of the combinations, I think. File length candidates for total return. So this is if the combinations pass the length of the candidates, or not if the combinations, if the loop reached all the possible elements, or the target is greater, the total is greater than the target. Appends candidates I to current and total plus candidates I. Increases the value of total. So it does that until the value is greater and then pops the element. And then increases the loop with the previous values. Pretty clever. But this part here is still not really clear to me. But I have to move on to the next one, so that's what I'm gonna do. I have to be careful to not spend a lot of time on each problem. So let's start 20 minutes. I think I'm gonna do this one more, and then I'm gonna stop here, and then continue after. Go read the book, and then continue after. Given an m times n grid of characters board and a string word, return true if word exists in the grid. The word can be constructed from letters of sequentially adjacent cells. Adjacent cells are horizontal or vertically the same letters. Letter cell may not be used more than once. Isn't this the same one that was used on the try tree example? So I have the board, and I need to figure out the number of boards. So I think the same approach is probably going to be used. And I have a RAS here. RAS, and then DFS, probably I, which is the count of the loop. I'm gonna do the same thing that he did there. No, maybe it has to be self.css, DFS. Not sure. Or maybe not, doesn't matter. Oh, def. The current is the one that is being tested, and then words. Or maybe W for words. So I have the board and a list of words. And it's a string words. Word existing in the grid. Now the difference is that I don't need to update the score and compare the values, obviously, because it's trying to find the words. So can I translate the logic of the previous one into this one? That's the question. So maybe I don't need another one, another list. You can just check on the same one if the values exist. I don't remember really well how he did it on the try, but I remember that he used the 4 different directions. But I don't remember how he used that to solve it. Because I remember he talked about for each element of the board, you check all the possible directions, and then on that specific situation he used the try to not repeat values or something like that. So what I've been thinking about is if I use a letter to compare, well, first I have to see if the letter is in the words. And then if I use that letter, I have to think about how to make sure that I'm moving to the adjacent ones. And that's the thing that I'm trying to think about. How I'm gonna do that. Or maybe I can just use plus and minus with the indexes. But I know it's gonna involve a recursive call at some point. This is the issue. So maybe what I can do is call recursively based on y. Yeah, I can have board here. Bars. Actually, I don't need to put bar there. For items, and boards, then I call DFS with items. And words here. And then here I have if cur, maybe I put item. If cur I not in W, return. So if the current letter is not in the W, I return, which is the words. But then how do I eliminate? Because the problem is I need to keep the index of the word. So maybe it's better to start. But if I check for the first, if it's the first letter of the word, then in the recursive call it's gonna break. Because I need to check if it is in the word or not every time, but I also need to maintain the integrity, which is the sequence that makes up the word, along with the board. Hmm. The try thing makes more sense, I think. Maybe it is the same, but then I don't understand why would this one would be on the backtracking. But overall, I think that this way that I'm doing things is good, a good way to do it. Because even though I'm not solving these problems now, is making it a lot more clear in my mind the gap between the things that I have to, the way that the solutions are for these types of problems, and the way that I'm first thinking about them. And I think the logic that I have to solve is not that bad. The main issue is understanding or thinking about ways to translate that into code because of the lack of understanding, lack of uh, proficiency, let's say, in recursion. Maybe I should just look at the solution for this one. Let's see if I can think about any other way. I think the only logic that makes sense here, maybe it's better to go off the word instead of the board. So take the first letter of the word, then search the board based on that letter. And then for each square of the board, check if it is the letter or not. And then check the adjacent ones for the remaining words. I think that's probably the logic to solve this. So you probably look for the word instead of the board, getting each character, and then you pass the character into a function. The function gets searches the board recursively. I think that's the approach here. I think I'm just gonna look at the solution because I'm not gonna have enough time to do this in 6 minutes. The next round that I'm doing, I think, yeah, like I said before, I'm gonna do hash, not 2 pointers first, 2 pointer problems, then linked lists, I think, and the easiest ones first, and then trees. And then I'm not gonna put a timer on because the timer also kind of demotivates
Hey everyone,
me
welcome back.
to type the code and try stuff out because I know I'm not gonna be able to solve it in 20 minutes if I type things out and stuff like that. So I think when it's time to go deep into each topic, it's better to not set a timer and pretend that it's impossible to look at the solution. And that way you force yourself to really try to think through and find any possible way that you can. And then once you are able to do that, and possibly your solution is not gonna be the best, because you're just trying anything that you can think of, and then you improve over time the optimizations.
Let's write some more neat code today. So today let's look at word search. This is a pretty good problem, and it's definitely very popular. So we're given a grid n by n with a bunch of characters, or you could say it's a board, and we're also given a target word, and we want to look for this word inside of our board. And if we can find the word, we return true. If we can't find the word, then we return false. And so within our grid, the word can be constructed any way, but it has to be either horizontally or vertically neighboring cells. So basically what we're looking for, let's say this is our board, we're looking for a path inside of this board where we can move horizontally, right? We're moving to the right, then we go down, and then we go to the left. So this is our path, and we are looking for a word. So we're looking for a path that can make this word. Down here, you can see in the example, they give us a target word, A, B, C, C, E, D, and that's the word we're looking for. We're looking for a path, and we can find a path with exactly those characters. Therefore, we can return true. Now, the question you're wondering is, how can we figure this out? Is there a really efficient algorithm to solve this problem? The answer is no. There's definitely not a super efficient one. We just are going to go through the brute force solution, and that brute force solution is going to be backtracking. So basically, this problem is actually pretty intuitive, right? How would you solve this problem in real life if you didn't have any code? Well, you'd go brute force, right? Let's start at every single cell. So we'd go through every single cell, right? Let's say this is an E, right? Does our word start with an E? No, it starts with an A. Now we have a C. Does our word...
I think the logic again,
or rather,
I got it down. That's pretty much what I was talking about. It's gonna search each word, but then the coding is the interesting part.
One thing I like to do with these problems is just get the dimension. So I'm going to get the number of rows and the number of columns. So get the length of the board, we get the number of rows, and get the length of the first row, and we get the number of columns. Also, remember how I said we can't revisit the same character twice within our path? Therefore, we're going to need a variable or a data structure for our path. We're going to use a set.
That's another key thing that I need to remember, which he did on the first problem as well, the try problem. Separating the rows and the columns based on the length of each part, getting the numbers.
To add all the current values from our...
Based on the length of the lists. That's kind of a difficult thing for me to wrap my head around. When you have a list of lists, to think intuitively which ones are the rows and which ones are the columns.
Board or positions in our board that are currently within our path, to make sure that we don't revisit the same position twice within our path. But other than that, if you've seen any of my backtracking videos, you know I like to follow a formula, so I'm just going to be going through that right now. So I like to create a nested depth first search function within the root or the regular function, because then we don't have to pass in some of the variables like the board and the word, because this is a nested function. But we are going to have to pass in the position of the board that we're at, so 2 variables, row, column for that. And we're going to have to pass in a third variable, I, which is going to tell us the current character within our target word that we're looking for. So if we ever reach the end of the word, or if I ever equals the last position. So if we ever finish the entire word, therefore we know we found the word, therefore we know we can return true, right? That's the good case. The other case is, what if we go out of bounds, right? Out of bounds of the entire board. What if row is less than 0 or column is less than 0, right? Or what if row is greater than or equal to the number of rows, or if column is greater than or equal to the number of columns? That's also out of bounds. So, or let's consider one more case. What if the character that we're at in our word, so word at position I, is not equal to the character that we're at in our board? So board at position row, column. So if this is the case, if basically we found the wrong character, then we also want to return false. And there's one last condition we have to check. What if the character, or what if the position we're at, row, column, this tuple, what if this row, column position that we're at is inside of our path set? What does that mean? That means we're visiting the same position twice within our path. We know all of these things that I've just listed, all these conditions are basically invalid. If any of these are true, then we have to return false, because, if we're out of bounds, we return false. If we see the same character twice, we return false. If we see a character that we are not looking for, we also return false. Okay, but once we're done with that, then we know, okay, we found
we found the character we're looking for, right? So what can we do? We can take our path and add the current position to it. So the current row column to our path because we found a character that we need. So now we're going to be continuing our recursive depth first search. And so we're going to be looking for the result of this depth first search. So we're going to run depth first search, right? We're going to run it in all 4 adjacent positions. So what I'm going to do is say row plus 1, leave the column the same, and add 1 to I. We're adding 1 to I because we found the character we are looking for. Now we're going to look for the next character, right? So now I'm just going to basically copy and paste this a few times. So I copy and pasted it 4 times because we're going to look at all 4 of the adjacent positions. So let me just fix this up. So you probably see what I'm doing, but basically I'm saying row plus 1, leave column the same, row minus 1, leave column the same, column plus 1, leave row the same, and column minus 1, leave row the same. So we're looking at all four adjacent positions. We're running depth first search on all of them, and if any of them return true, then our result is going to return true. Remember, we only need to find our target word one single time. So if we ever find that word, then we know we can return true. So I'm going to go ahead and return that result, but right before I return that result, I'm going to do a little bit of cleaning up. So I'm going to take our path variable and remove from it the position we just added to the path because we're no longer visiting that position, right? We're returning from this function called, therefore we don't have to continue to visit that position inside of our path. So this depth first search recursive function is always the main part of the backtracking problems. Once we're done with this function, the only thing left for us to do is actually brute force, go through every single position in our grid and run this depth first.
Yeah, these parts here are the ones that are difficult to think about because you have to think from the end of the function and the recursive calls, what's gonna happen on each one. But yeah, and the confusing thing for me when problems that involve matrix is thinking about the rows and columns as you were moving through the matrix. Because the first approach that I think in my mind is doing a nested for loop, which is obviously not good. So this one, it's a lot better. It's probably a good thing to remember. Because the way that I was thinking about, and I knew that it probably wouldn't be the best, it would be to create a nested for loop and then use I and j to get the position of the letter in the thing. But this way here seems much better because obviously you're not doing O(n) square inside of this function, which is a lot better. And then you're using the set to keep track of the path. So if the values are lower than 0, it means that you reach the end of the column or row. If r greater or equal to rows, and this is for the other one when you're summing. Same thing, you're checking the boundaries pretty much of the board. Or word I different than word RC. So the word that is currently checking is different, returns false. And that's the thing that I don't understand, I think. That's the issue that I'm having. Or RC path. So if you already visited the nodes, I think, the path. The issue that I'm having is understanding what is going to be this res value here. What is going to be the return of these functions, because it's returning false or true each time. But then how does that logic works here? That's the thing. Also, I think he's using the set as a stack. So he's adding a specific row and column. And then testing all the possible combinations for that. And then removing. But then again, because each time it's going to add a different combination. Yeah, so I think, yeah, it makes sense because you're walking through the board. It's very difficult to think about it.
For search function on it. So that's exactly what I'm going to do for every single position, every single starting position in our board. I'm going to run depth first search, passing in the row column, passing in 0 for the position of I because we're always starting at the beginning of the word. And if we ever return true, if this depth first search function ever returns true, I can immediately return true from our function exists, right? I can just return true immediately. I don't have to wait. And if we never return true, if this goes through every position in the board and we never return true, then I'm going to have to return false out here because that means we did not find the word that we were looking for. So this is the entire function actually. You can
so he does use the nested for loop here at the end. It's just a different way to think about it. And again, is the problem with the recursion thing because I was thinking about doing inside of this function, and it does outside. And the main issue is understanding this return value here of these recursive calls. So I think the main focus for me after I finish the blind 75 is going to be diving really deep into recursion and trying to be really good at it.
That it's definitely not very efficient, right? We're running through the entire board, right? So what's the time complexity of that? Running through the entire board is going to be n times m, because those are the dimensions of our board, and that's being multiplied by the depth first search function, right? Because we're calling that depth first search function every single time for every position in the board. So the question becomes, what's the time complexity of the depth first search function? Well, the call stack of that depth first search function is always going to be the length of the word, right? Because the word can only be so long, we can only go through so many characters for the word. So that's going to be the call stack of it. Remember, though we have 4 different branches, we're calling the depth first search 4 different times. So it's really going to be 4 to the power of the length of the word that we are given. So it's going to be something like 4 to the power of n, where n is the length of the word. So you can see this problem is not very efficient. So let's just clean this up. So this is going to be 4 to the power of n roughly, right?
And I think I need a good way to visualize all the possible, what value this function call, this recursive function call is going to return before. So, because that's usually what I do when I'm solving other problems, is picturing instead of this function here, I had all the possible values that it returns after it goes through all the recursive calls, before it goes into the other recursive call. If I could picture that in my mind, know exactly which values are going to be here after it goes. Because in my mind, I think the execution goes line by line into this function, and then it gets through here, and then it goes back into this, and does this recursively. But then it's different because along the way you can have different values that are gonna make it go more times before it goes forward into the next recursive call. And that's the difficult part, I think, to visualize. So maybe there's someone out there with videos that will help me, and probably the books as well, help me visualize into what's happening under the hood with these recursive calls. I need to clarify that more in my mind.
Right? So it's not a very efficient solution. This is the rough time complexity of the problem. So I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching.
So I think I'm going to stop here and word search. Word search. Now we get into graphs. Nice. Hopefully I can get to 50 today, or even more. Would be great. So I'm going to stop here, and I'm going to read the book, and then we'll come back soon to keep doing this. So see ya.